Okay, I'd like to thank the organizers for inviting me. It's my great honor. And for those of you who don't know where I am, it's in Tsinghua University, which is in northwestern part of Beijing. And here's sort of a map of it. We are next to the old Summer Palace, and we're also next to a place called Center of the Universe. uh, and uh, and I'm affiliated with two sort of departments, and there's a Tsinghua version of the IES, and also there's also a department of astronomy, which is just 1 month old. Before it was a Center for Astrophysics in the physics department, and also very close by is the KIAA, the Kavli Institute from Peking University, and altogether we have a really decent group of people. In particular, this is Doug Lin, who is a visiting professor at Tsinghua IES, and Chris Ormel is going to join us in just a couple months. And so we have a really, we're developing a strong group towards a strong group on exoplanet planet formation. So I think I'm the only person in this session. Presumably it's the session for gas dynamics. So my hope is to cover the following 4 topics: angular momentum transport, and sort of as a consequence of that, gas kinematics and their influence on the disk structure, broadly defined temperature structure, density structure, etc. And eventually, I'm going to briefly discuss about the long-term evolution and dispersal. All right, so before we really start, let's talk about what's the governing piece of physics, okay, in gas dynamics. So starting from the thermodynamics, I think if you naively assume that, well, if the disk is viscously accreting, and given the typical accretion rate of, say, 10 to minus 8 solar masses per year, and you arrive, and with typical, say, opacities, mass, etc., you arrive at a mid-plane temperature of order, say, 500 K at 1 AU, and that goes as more or less R to the minus 1. And in the meantime, the disk is heated by the star, by stellar irradiation, and the irradiation temperature is something like 300 K or ish, but it decreases with radius much slower. So that means the bulk of the disk has to be irradiation dominated, so the temperature is mostly set by irradiation. That sort of makes the study of gas dynamics relatively easy because you more or less know, given the distance, you more or less know what the temperature is. But the innermost region is likely dominated by viscous heating. This is true particularly when the temperature reaches, say 1,000 Kelvin, then you trigger the ionization of alkali species. And there, you basically, the MRI must be active, and you get a lot of turbulence. And these turbulence generally are sufficient to generate enough heat to sustain, so that the temperature in this region where we have thermal ionization is really dominated by viscous heating. But and exactly where this transition happens from viscous heating dominated to irradiation dominated, then that really depends on the gas dynamics, say, basically beyond this thermal ionization region, etc. And in addition, the bulk of the disk, as I said, is mostly dominated by irradiation. But in addition, there are also high energy photons, X-rays, and UV. They can essentially heat the disk atmosphere so that you get a cool sort of mid-plane bulk disk, and then you get a much hotter atmosphere. So that's a very brief summary of the governing physics that determine the disk temperature. And another piece of governing physics, which I think is probably more important and also is very widely discussed, is how do magnetic fields and gas are coupled. And we know magnetic field plays a crucial role here. So here, how they are coupled, well, magnetic fields are only coupled with the charged species, so that has to do with ionization. Here, unless, besides this region where you get some thermal ionization, the bulk of the disk, again, has to rely on external sources of ionization here, mainly the stellar X-ray UV, and possibly some cosmic rays if they are not being excluded by, say, stellar or disk winds. And if you take some typical parameters from, say, the stellar X-ray flux and cosmic ray flux, etc., and you plug into a chemistry calculation, and here is a ionization fraction, just look at the red line, as a function of height above the midplane. So you are talking about ionization fraction of something like 10 to minus 14 at 1 AU in the midplane region, and that only increases to 10 to minus 8, minus 7 towards the surface. So you're talking about extremely weakly ionized system. And in this system, gas and magnetic fields are not well coupled. And how do we describe this coupling? So starting from the simplest case, where if they are very well coupled, if the gas is well ionized, then you have this very familiar result of flux freezing that's called ideal MHD. So that means if you move the fluid around, then magnetic field moves with it, and that's described by ideal MHD. And if you're very weakly ionized, then what happens is that, okay, you have charged species, electrons, ions, and electrons are the most mobile species. And what electrons do is that they just gyrate around the magnetic field, and from time to time, it can collide with a neutral molecule. And after one collision, they sort of jump from one field line to another. So basically what happens is that field lines are frozen in the electron fluid, okay? And on top of that, because of this electron neutral collision, they can, they sort of, magnetic field can slip through these electron fluid due to these collisions. And another way to freeze this, and these are described by non-ideal MHD. And these are probably the only equation that I'm going to show. And the way to describe this, this non-ideal MHD effect, is you just look at the induction equation. Here, in the non-ideal MHD regime, magnetic fields, they are only frozen to the electrons. And plus that electrons can collide with the neutrals, that gives you this dissipation term, this is the resistivity. But of course, when you solve MHD equations, you're not really solving electron velocity. You only solve the velocity of the bulk fluid, which is basically the neutral, velocity of the neutrals. Then you play this mathematical game. This is identity. You say electron velocity is a bulk fluid velocity, well, basically the neutral velocity plus electron ion drift plus ion neutral drift. And so this is identity. And when you plug them back in, you get, so this induction equation is split into, now you get this more familiar inductive term, that's the ideal MHD term. Then you get this 3 extra terms. So this just copied from here, the ohmic resistivity. And then the electron ion drift gives you the Hall effect, and the ion neutral drift gives you this amipolar diffusion. And if you look at how, and these are called non-ideal MHD terms, and if you look at how strong these terms are, you figure that they are all inversely proportional to the ionization fraction. That means, the weaker the ionization, the more important they are. And in addition, you see the amipolar term is proportional to B squared over rho squared, and Hall is proportional to B over rho, and ohmic is independent of B over rho. That means this amipolar diffusion is going to be important in low density regions with strong magnetic field, and ohmic is basically the opposite limit. It will be important only in the densest part of the disk. And another thing to notice is that this Hall term has a very interesting property, which is polarity dependent. And the way to understand it is, again, looking at this equation and you ask what happens if you change the sign of the B field. Let's say if you basically flip the field. And the first thing you might want to check is whether the Lorentz force changes or not. But fortunately, it's not, because if you change sign J, it's curl of B. So they change sign twice. Lorentz force is not affected. But what's affected if you look at the induction equation, if you change the sign of magnetic field, everything changes sign except the Hall term. So that basically makes this term a polarity dependent term, right? So that when you, so depending on whether the background field is, say, aligned with rotation or anti-aligned with rotation, you can get different, they can affect the evolution of magnetic field differently, and hence it affects the overall dynamics differently. And now we ask, in disks, which regions are dominated by what effect? As I said earlier, right, ohmic resistivity is important in the densest part of the disk. That applies to the midplane region of the inner disk. And then as you move up, as density drops, you are then dominated by the Hall effect. And as density drops further, if you move up further, you are dominated by amipolar diffusion. And eventually, to the very surface layer, there's a far UV can penetrate into the disk, and they can substantially boost the ionization fraction, so that since the ionization fraction has boosted substantially, you bring the gas into more or less the ideal MHD regime. So that's in the inner part of the disk. And if you move radially outwards, again, as density drops, the ohmic resistivity becomes unimportant. Now you are dominated by Hall in the midplane, and move up, then amipolar diffusion, then ideal MHD. And if you move radially outward further, then you are entirely dominated by amipolar diffusion. So that's basically the scaling, how important these effects are in disks. All right, so now let's talk about angular momentum transport. there are basically two ways you can transport angular momentum. One is by transporting angular momentum radially outward. Okay, this has to do with either you have some sort of viscosity. Normally, you don't have real molecular viscosity, so you need some kind of turbulence, and that normally is thought to be either the MRI or pure hydrodynamic turbulence. But in fact, when you have magnetic field, you can also have a sort of laminar stress, which is essentially the same as magnetic braking. That can also transport angular momentum radially outward. Alternatively, you can transport angular momentum vertically and by a magnetized disk wind. This requires some large-scale magnetic field threading the disk. And as the disk rotates and it's differentially rotating, you can wind up magnetic field into this helical configuration that you build up magnetic pressure, and then that can push things out. And in the meantime, magnetic fields don't want to be winded. They want to straighten. Okay, so when you wind them up, they try to resist. And when they resist, they extract angular momentum from the disk. Okay, so in the meantime, as you launch the wind also extracts disk angular momentum. For this, okay, we see that in both cases, in general, you need some sort of magnetic fields. Okay, but here, for this case, MHC mechanisms are sensitive to ionization. Okay, you have to do with how well they are coupled. The hydrodynamics mechanisms are also widely discussed, and they are found to be very sensitive to thermodynamics. And for MHC wind, the wind properties, okay, these are also widely studied, but they are found that the wind properties are sensitive to disk physics. So in either case, we really need to have a realistic understanding of the disk physics before we can understand angular momentum transport. All right, and here's, because there have been so many works already, and so I just give a very quick summary of what people have done. Okay, so back in the 1970s, the viscous accretion theory was sort of developed, though at those times they're not motivated by protoplanetary disks, but by X-ray binaries. And then but at that time, it is well known that, okay, if you have viscosity things, everything works, but where is the source of viscosity, that was unclear. In the 80s, the theory of MHC wind was developed and was sort of very popular at that time because people don't know what's the source of resistivity, but you have a working model, which is disk wind. And then in the 90s, the first thing is that MRI was rediscovered. And then immediately, while people find the source of viscosity, then there's a sort of paradigm shift. People now all work on MRI. In the context of protoplanetary disks, GAMI proposed this layered accretion model. And those are mostly based on there are 3 MHC effects. They are all well recognized, but at that time, mostly people only considered resistivity. And so those are all in this regime of layered accretion because resistivity only in the inner region of the midplane region of the inner disk. So the inner disk is layered accretion, outer disk, people thought is all MRI turbulence. Wind theories were continuously developed, but at a slower pace because more people are working on MRI-related stuff. And then in the in the past decade, Hall effect and ambipolar diffusion become better understood. That's mainly thanks to simulations. Okay, when people can start to understand the nonlinear outcome of the MRI in the presence of Hall effect and ambipolar diffusion, and the main result is that people find that in the inner disk, MRI is completely suppressed, and you have to rely on wind-driven accretion to drive angular momentum transport. And so the wind picture scenario is revived. And in the meantime, several hydrodynamic instabilities are identified. So there's also a resurgence of studies of hydroturbulence. And there's a nice review very recently by Vlad and this Umarhan. And also in the meantime, thanks to the computational development, people now are able to run global simulations that include all 3 non-MHD effects. And so based on all this, okay, here's a very sort of my own personal sort of a little biased summary of what's our current understandings. So this region, we have thermal ionization we expect to be fully MRI turbulent. And then in this bulk inner region, thanks to all these non-MHD effects, MRI is suppressed. And you have this MHD wind. Because of the Hall effect imported in this region, so the property of the gas kinematics depends on the polarity of the large-scale magnetic field. Okay, and in the outer region, it's only ambipolar diffusion. Ambipolar diffusion should be sufficient to damp MHD, but not necessarily fully suppress it. So you expect some damped turbulence. And then also there's a surface layer that if FUV is able to penetrate into the surface, that may give some stronger turbulence toward the surface. So that's the sort of current understanding. And here I'm showing you the recent global simulation that include all three non-ideal MHD effects. And of course, things depend on the polarity, so I'm starting with the aligned case where background field is aligned with rotation. Okay, so I have three panels: density, mass flux, and magnetic fields. The first thing that you may notice is that the field get amplified. This is the color is toroidal field. And this is due to the so-called Hall shear instability that has been also discussed in the literature, which happens in this aligned case that strongly amplifies the horizontal component of the magnetic field. Because this region Hall effect is stronger than towards the outer region. So here the B phi is amplified so much that it actually occupies the entire disk. Okay, but on the other hand, to get the right wing geometry, B phi must change sign. So it has to change sign somewhere. So in this case, it changes sign in the surface. But towards the outer disk, because Hall effect is weaker, they are able to change sign, sort of getting a more symmetric configuration. They change sign in the midplane region. And then more interesting, if you look, from there, if you to look at the mass flux, clearly you can see here, red means mass is moving out, blue is moving in. And you see that in this region, you have sort of half of the mass moving out, half moving in. Okay, in this region, you get all the accretion flow in the midplane, but you get above and below, you get mass flowing out. And why is that? This is entirely due to the magnetic field configuration you get from the third panel. And the way to understand it is that, okay, so you have rate of angular momentum loss equals the torque, and the torque is from the Lorentz force. Okay, and here's the rate of angular momentum loss, the specific angular momentum, the differentially, and the times the accretion velocity. And on the right hand is the torque. Torque is from Lorentz force, okay, and here is the z component, okay, of the F over F cross R, right, the torque. And that has to do with the phi component of the Lorentz force, and if you go through all this, you find that it's basically the depends on the vertical gradient of B phi, okay? So that gives you the J cross B, okay, is the Lorentz force. So it's this one and times BZ, that's the dominant component. And when you equating this two, you find that basically this VR, the accretion velocity, is proportional to the vertical gradient of B phi, okay? Okay, and BZ, if the disk is thin, BZ is more or less constant. And so now if you look at here, right, in this region, B phi maximizes at the midplane, right? So the gradient of B phi changes sign across the midplane. So that's why the direction of the accretion flow changes sign here. And in this region, B phi the gradient is strongest here, and it changes sign in the direction such that you get accretion flow. And then B phi increases and decreases, so you get the first increase is you get this accretion flow region, and then decreases you get this outflow region. So that's how you can sort of understand this complex flow structure. And actually, this complex flow structure may have some implications on dust transport, right? Like in this region, if the dust is just doing some vertical oscillation, you have some turbulence, but if it's upper half, the gas just carries the dust outward, and in the lower half, the gas carries the dust inward. We find that in this case, this complex flow structure more or less acts like diffusion. Okay, so it just give a little bit of extra diffusion that will mimic this effect. But in this region, it's actually more interesting because the dust spend more time near the midplane region, so that this will actually give you some accelerated radial drift. So the dashed line is that if you don't consider this complex flow structure, you get the dust evolution that behave like this dashed lines. But if you can take into account this complex flow structure, you get a much faster drift. Okay. All right. Okay, that's the aligned case. And here, another simulation is the anti-aligned case, where net field is anti-parallel with omega. And in this case, everything works the opposite way. Instead of Hall shear instability that amplifies the field, then they try to reduce the field. Okay. But it turns out this configuration is a little unstable, and eventually you end up with a highly asymmetric configuration where B phi changes sign at the very disk surface. And whenever B phi changes sign, you get a very strong accretion flow. And that accretion flow is exactly at the mid disk surface. And that's one-sided, asymmetric. And in fact, it's actually, we found the accretion velocity is supersonic. So you get also sort of this kind of behavior, but they are all understandable once you understand the magnetic field evolution. All right, the next topic is about the level of turbulence. And as I mentioned before, right, we expect the, well, in terms of observations, you can only probe the outer region. And in the outer region, the expectation is that you have damped turbulence in the midplane. And the surface layer, you may get some MRI. However, observations tend to show that this is for HC 163296 from Flaherty et al. And people tend to find that, okay, anywhere, okay, they are using because different lines have different optical depths so that they can probe different vertical heights. But looks like at all region, you only get upper limit, and very stringent upper limit, well below 0.1 sound speed. And the same seems to be true on the other disk, TW Hydra. And this work led by Jake Simon. And in order to reconcile this result, we find that we really need somewhat weaker field. And also, we need to reduce the ionization level. And how to reduce ionization level, there either when cosmic rays are excluded and X-rays may be shielded from the wind launched from the inner region. There are some ideas, but this needs to be tested. All right, now moving to the discussion of pure hydrodynamic instability. Since this is a review talk, I'm just briefly covering this, but I believe there are people in the audience that know much better than I do. There are three major hydrodynamic instabilities that has been intensely discussed in the recent literature. One is the vertical shear instability, which is natural in disk because the disk naturally has a vertical shear in the azimuthal velocity. And whenever you have that, as well as fast cooling, okay, you would this vertical shear instability will turn on. And then there's also the subcritic baroclinic instability, which subcritical means it's nonlinear. But there's also a linear version called convective overstability. They operate on similar mechanisms. And this basically requires a negative radial gradient. So it's like a convection, radial convection. But of course, it requires some assist from thermal relaxation. If it's a purely adiabatic, this won't work. You need some thermal relaxation to allow some heat exchanges for it to operate. And then there's a more exotic zombie vortex instability. It's also a nonlinear instability and needs some seed vortex to operate. But this one needs nearly adiabatic conditions. And here, this is a review, recent review by Vlad and Uckerman, showing the possible regions of where these instabilities may show up. And so since this one requires highly adiabatic conditions, so this may reside in regions with highest optical depths. And vertical shear instability may operate in the outer part of the disk. And if you manage to set up a radial pressure gradient, radial entropy gradient, then you may have convective instabilities in between. And these different instabilities have different properties. This VSI have primarily show this pronounced vertical velocity fluctuations. And the baroclinic or the convective overstability showing a lot of big vortices. No, well, not big, actually small vortices. And the ZVI, the zombie vortex instability, also start with some vortex, but later on it can evolve into this kind of so-called zonal flows. But nevertheless, all these instabilities seem to, they all seem to transport angular momentum, but only at modest level, typically with alpha values less than about 10 to the minus 3. Well, the next question, a natural question to ask, is whether they survive. Okay, so these are all mostly discussed in the context of pure hydro. Okay, then the question is whether, if you have MHC wind, there's a magnetic field, and there's some coupling between gas and magnetic fields, whether these instabilities still operate. So we start to look at this problem. We just pick up VSI. and we'll try to study the interplay between VSI and magnetic fields. And there has been one study on the linear stability of the system where, people find that if you have MRI, basically VSI is suppressed. But of course, if MRI is not suppressed, and we're just trying to see what happens, so this is simulation. We are setting the cooling time to be 0, which is ideal for VSI. And clearly, it launches this wind, but in the meantime, you can see this is a V theta, or basically a VZ. And clearly, you develop this very characteristic VSI patterns. And then it perturbs the disk, but the wind and this VSI can definitely coexist. We also played with different field strengths, and when field strength is weak, the property of the VSI is basically the same as pure hydro simulations. But when the field gets stronger, it basically modifies the vertical shear profile, and then the properties are slightly different. All right. Now I'm going to move to about the kinematics of the wind. As Kathy has already given a very nice review on this so-called photoevaporation, and the photoevaporation is based on the idea that if there's no magnetic field, and then the disk surface is heavily heated by the high energy radiation so that you can launch an outflow, the gas becomes unbound. And there are 3 flavors, UV, far UV, X-rays. And far UV and X-rays can typically give you a significant mass loss. And there's also another flavor of external photoevaporation. But in the meantime, if you have magnetic fields, this is sort of the development of MHD wind over the past 20-ish years. But mostly, when people talk about MHD wind, people talk about cold MHD wind. That's also mostly what simulations, their parameters are tuned for. And this kind of wind, typically, they require strong vertical field. And actually, if you use that parameter space, you find that the wind is way too strong for prototype radius. You will basically lose your disk in, say, 1,000 years instead of a few million years. And because you have such strong field, the wind is typically in the centrifugal regime. The magnetic field lines are very stiff, and so that anything on the gas will be flung out by the centrifugal force. But I would say, really, these two things should not really exclude each other. We really need to marry photoevaporation with MHD. And so that's what we proposed a sort of unified picture where, yes, you are using, you have MHD wind, which drives the accretion. Photoevaporation doesn't transport and it doesn't drive accretion. You have MHD wind, but because the wind is heated, this region is heated, so the wind is hot wind, it's not a cold wind. And the level of heating may likely affect the gas kinematics. And here's some sort of a semi-analytical model, and here I'm just showing the 2 main parameters in that simple model is the magnetic field strength and how much far UV is able to penetrate. And we find that, if you increase magnetic field strength, wind-driven accretion rate increases, and wind mass loss rate also increases, but it increases more slowly. On the other hand, if you, say, increase the far UV, here it's just parameterized by far UV penetration depth, wind-driven accretion rate increases, and mass loss rate also increases, but it increases a lot faster. So basically, both magnetic field strength and thermal effects matter. And so we call this magnetothermal wind as a purpose. We just try to marry the 2 processes. And we also find that the disk, the mass loss rate from this wind is actually fairly significant. It's comparable to the wind-driven accretion rate. And also, and in this case, the wind driving mechanism is not a centrifugal. It's not a magnetocentrifugal wind that people usually talk about. It's mainly the wind is driven by magnetic pressure gradient. All right, and but of course, because the wind sensitively depend on thermodynamics, right? You really need to get the thermodynamics right in order to get realistic wind properties. So, but to get the thermodynamic right, you need to get cooling right. To get cooling right, you have to get the right coolant, so you have to get the right chemistry. And this is the work led by Lila Wang, and where he was able to implement time-dependent chemistry, which is quite impressive, and couple that with MHD. And you get very nice wind launching, and everything is self-consistent because the thermodynamics is self-consistently computed. And here, I think Jeremy is likely going to talk more about this work. But just to show that here you get So this is a wind-driven accretion rate and mass loss rate as a function of radius. So you get the right accretion rate of about 10 to minus 8 solar mass per year, and the wind mass loss rate is actually also significant. It's about comparable to the wind-driven accretion rate. And moreover, Lila has found that EUV actually can be important. And also wind heating is actually dominated by ambipolar diffusion because the wind is not completely ideal MHD. There's also some ion neutral friction which hits the wind. And in terms of chemistry, right, in order to make this calculation possible, you cannot really use a very complex chemical reaction network like the astrochemistry people really use. And so to make this possible, you really need a reduced chemical network. Otherwise, it's hopeless. And so we are with Rui Xu, who is currently a student in Princeton. We made an attempt to do this. And you're not supposed to read all these, but basically we're able to reduce a chemical reaction network from, say, several hundreds of species, several thousand reactions to, about 30 gas phase species and 60 gas phase reactions. And that they can reasonably reproduce the result from much complex chemistry. But this only works either in the midplane region, say within plus minus 2 scale height, or in the disk atmosphere, which is penetrated by UV. The intermediate region turns out to be very complex, where you have rich molecular chemistry, and those you seem to need about 100-ish species, which that's probably the major difficulty if you really want to couple chemistry with dynamics throughout the entire region. All right. Another aspect on disk structure. Because, well, substructures are now seems to be ubiquitous in disks, right? And there's a natural debate whether the substructures are caused by planets or they're planet-free mechanisms. I'm not saying that they are not necessarily planet-free, but in the but people do have discussed several possible mechanisms that magnetic field can induce these substructures. And one of them is the so-called zonal flows, which is found that, so this is the time evolution of a local shearing box simulation. And this is time, and this is basically the radial direction. And you can see what's plotted here is the midplane density. And you can see as time evolves, it automatically, spontaneously develops into this banded structures. There's density variations, eventually merge into one big sort of density bump plus a trough. And what's more interesting is that if you look at the time evolution of magnetic flux, you see that magnetic flux get concentrated in this gap regions. And in just last week or so, I think there's a paper showing that this is actually likely a wind instability. Basically, if you have a slight more concentration of magnetic flux here, you tend to drive a stronger wind, and then you deplete this region more, and also you transport angular momentum a bit more, so that also helps it deplete this region. So this is one possibility. And another possibility is work by Suriano et al., and also there's discussions by Bessun et al. Basically, you have, these are mostly ambipolar diffusion-dominated disks, and there's they found that a mechanism where, when you have this wind-driven accretion in ambipolar diffusion-dominated regime, you have accretion flow mostly concentrated in the midplane, and that accretion flow drags magnetic flux, and at some point they reconnect, and after they reconnect, you get a region devoid of magnetic flux, and that becomes the density bumps. And in between, you have all this magnetic flux, which tries to deplete this region. But empirically, this only seems to work when you are modestly strongly magnetized with vertical plasma beta less than 1,000 or so. These are actually fairly strong fields. In typical MHD simulation, we have vertical plasma beta of 10 to the 4 to 10 to the 5. So this is a bit on the stronger side. And there's also recent work by Xiaohu, who is also here, et al. And they found that if we, instead of having a uniform prescription of the ambipolar diffusion coefficient, what if, say, the dust distribution is there was the result of sintering when HL tau result was coming out. There were multiple explanations. One of this is a sintering result basically near the snow lines. The dust they tend to produce more smaller dust particles due to sintering because the dust particles become more likely to fragment. And so you get a smaller, a stronger non-ideal MHD effect near the snow lines. And when you plug that in, they seem to find, okay, you tend to also produce substructures near here are the two major snow lines that they included in the model. So all of these they're not necessarily conclusions, but these are all the possibilities that are currently available in the market. All right, there are also, the next topic is about the temperature structure. Usually people do this in either two ways. In the post-processing manner, you just say, okay, we can run very complex models with the radiative transfer and possibly thermal chemistry as well. Everything is included in a static disk model. And you can also possibly add viscous heating, assuming everything is viscous. And here you get some temperature profile. The surface layer is very hot. And the mid-plane region, if you include viscous heating, you can get a mid-plane region that is hotter than the intermediate layer, and then eventually surface you get superheated. There are also relative radiation MHD simulations. Usually they're either fully in the ideal MHD regime or include some resistivity in the mid-plane region for the dead zone. Those you can get the temperature sort of viscous heating. If you have some viscous heating, you get some little bump here. Otherwise, it's more or less flat, and then they raise up. Well, the nice thing about this is that you take into account the turbulent dissipation profile. Although in this particular model, the turbulent dissipation doesn't seem to be, well, it seems to raise the mid-plane temperature by a certain amount if you have some turbulent dissipation. But now, if we are in this pure wind-driven accretion scenario with no turbulence, then you have no turbulent dissipation, and instead you have some geodissipation. Okay, we have resistivity. It's just J cross J dot E, and then we did a calculation with Shoji Mori at Tokyo Tech where we included geodissipation, and we see what happens. And we found that geodissipation is very ineffective, and so that basically the bulk disk temperature is almost entirely determined by irradiation. Okay, and instead, if we include alpha disk model with alpha, relatively large alpha, you get a mid-plane temperature bump. But since we don't have that, okay, in reality, you just have geodissipation. Then we find that mostly the disk temperature is entirely determined by irradiation, and that's generally cooler than what people usually assume. All right, I'm almost running out of time, but I still have one important topic, which is on the long-term evolution. Because all the what I've talked about relies on the fact that you have some large-scale magnetic field flux penetrating into the disk. Okay, then the question is where that magnetic flux is coming from and where does it go? Okay, and this lies into the problem of falls into the problem of magnetic flux transport. And conventionally, that's understood as a balance between accretion, which try to advect magnetic flux inward, and then if you have dissipation, either turbulence or resistivity, that tend to diffuse magnetic flux outward. And whether you get flux transport flux in or out depends on which of the effect wins. But now we don't have much turbulence, and also we have other non-ideal MHD effects. So the question is which direction, okay, does magnetic flux move? So earlier we did some numerical experiments. These are applicable for the outer region of the disk, but you still include the Hall effect. And in both cases, we find that magnetic flux, in both cases, they all move out. Okay, it's just in this case, I think it moves out faster than this one. And if you combine all the results together, we find that in all cases, you move magnetic flux out, and the more strongly magnetized, the more rapidly you are losing magnetic flux. So in terms of time evolution, overall you are losing magnetic flux, and initially you are likely to be more strongly magnetized here, and you also lose magnetic flux faster. Okay, so that you evolve towards this region, then you get more weakly magnetized. You're also losing flux, but you're losing more slowly. Okay, so that's sort of I would say consistent with the fact that when you are your early, say, class 0, class 1 phase, you are very rapidly accreting, but these phases are also relatively short-lived. Okay, and then the later phases, class 2, you are less magnetized, but you're also losing flux slowly, more slower, and so you are more likely to be long-lived. But there's another complication because all the disks have an outer boundary. They are truncated. So that now recently I'm working with my postdoc, Haifeng Yang. We are running simulations with the outer truncation. And interestingly, we find that, okay, you're actually not really losing magnetic, you're reconnecting magnetic flux. So magnetic flux, they first bend, okay, then they close somewhere there, and then you form a loop, and this loop gradually shrinks. Okay, so that's probably how magnetic fluxes get dissipated, okay, in disks. All right, I'm just finally briefly mention that we don't have much magnetic observations on magnetic field because I think the only one that's currently published is this upper limit from the Zeeman splitting by Fleming et al. For the TW hydra disk. But the result can be debatable because there are systematics that may be underestimated. But the more reliable measurements, I would say, is probably coming from the solar nebula, paleomagnetism. Basically, they're just studying magnetized meteorites. And you have to find the right sample. They are very pristine, and they are well preserved so that they may have the nebula conditions. Here's a compilation of currently measured paleomagnetic samples. And also the nice thing is that you have radioactive ages, right? So at about 2 million years after CI formation, that's roughly the age, okay, of the time 0 of the solar system, you get a very relatively stronger magnetic field here. And over time, it seems to be decaying, and eventually you only get upper limits. If you can compare the measured field strength with the expected field strength, okay, basically the stronger the field, the higher the accretion rate is, so that the expected field strength is parameterized as a function of accretion rate. And here different lines are for different sort of mechanisms. And more or less, I would say they are all sort of compatible with the expected accretion rate of about 10 to minus 8 solar masses per year. So far, this seems to match reasonably well. All right, so let me summarize. Angular momentum transport in disk is likely wind-dominated and with possible contribution from hydrodynamic instabilities. The flow structure can be complex and depend on the polarity of the large-scale B field. The disk wind is magnetothermal in nature with significant mass loss comparable to accretion rate. This might yield ring-like substructures, but it's of course debatable, and with very little heating. Okay, the Joule heating is very inefficient. The long-term disk evolution is likely governed by the transport of magnetic flux, and which they are transported outward, and magnetic flux get dissipated over time. Since this is the talk on computation, I haven't really talked anything about computation, but here are I would say here are the necessary ingredients that we would love to include in model 9 MHD. Radiation, especially important in inner disk and also in the early phases of disk where it's highly optically thick. Self-gravity, chemistry, and particles coagulation. I would say so far, hardly more than 2 of the above have been included. And so that also means that there's a lot to be done. I'll stop here. Thank you.
Questions, Jake?
Yeah, so I just wondered if how many of these simulations were 2D versus 3D, and can you speculate on if anything would change in 3D?
All the simulations I showed are 2D.
Mm-hmm.
So one thing is that once you form this current sheet, I'm not sure whether they're stable, and that has to be examined in 3D. But 3D simulations do exist. Well, actually, for the ring simulations that I mentioned, I think both Xiao simulation and Suriano simulation, they all went to 3D. Although I would say the resolution, I think their resolution is very poor in 3D. Xiao's resolution with mesh refinement is okay. But I think they find consistent results between 2D and 3D. Yeah.
Kathy?
Extent of your wind-driven region. I noticed a lot of your calculations were going out to about 50 AU, and you mentioned an ambipolar diffusion dominated region beyond there. Just given that most of the mass in a disk is at large radius, how far out can you get this mechanism to work?
Well, let's see. Yeah, like this simulation, I mean, the disk goes to infinity, basically. It goes all the way to the outer boundary. There's no truncation. And I couldn't manage to get the simulation because, like, say, you have one rotation at r equals 100. That means 1,000 rotations at r equals 1. And I couldn't afford to run that too long. And so at least I would say up to this radius, I'm very comfortable. Okay. Yeah.
So why the flow that is created by the whole shear instability is not affecting the density perturbations when you have the BSI? When you show this slide where the winds does not affect in principle the BSI.
Oh, the VSI, okay.
But then when you have the whole shear instability, you are producing these asymmetric flows at the midplane. Why that is not affecting the density perturbations?
Okay, so for this simulations, I didn't include Hall. It's pure ambipolar diffusion. And I would also call this a numerical experiment. We're actually playing some tricks that we are making sure that we are in a reasonably clean environment. You have a pure ambipolar diffusion dominated regime with a laminar wind, and then you see whether VSI can develop. But of course, yeah, eventually we need to do more realistic simulations. Yes.
Just take one more question.
So in the anti-aligned Hall case, it looked like there was a kind of turbulent VRs in the center. Is that just an artifact of a different
You mean
scale?
what? You mean this region is?
Yeah. Is that normal turbulence?
Yeah, this is something that I need to go to 3D to better verify. I think Jake also had some local simulation that in this anti-aligned case, you get some turbulence. Yeah.
And it's stronger than in the aligned case. The fluctuations, not
the fluctuation. Yes, because the aligned case is basically laminar.
Yeah.
Okay. Yeah.
Okay.
Did you mention the concept of a Hall dichotomy at any point?
Say again? Hall
dichotomy. I mean, there was an idea
Hall
bouncing
dichotomy.
around that maybe
yeah,
totally different types of disks out there
right.
that we should be finding.
Yes, I should have mentioned that. Yes. I haven't mentioned anything related to gravity. I think Kathy already did a great job. I haven't mentioned, but those are relatively in the very early stages. And yes, in terms of initial conditions, which Tew also mentioned.
Oh, so you're thinking that?
I haven't talked anything about initial conditions. Yes, that's another important topic.
I was thinking,
but
the
yes,
idea that disks, there might be two of evolved disks. There might be ones that had aligned and anti-aligned that would behave very differently in observations.
Yeah,
and
that's entirely possible. Yes, they are maybe they are not born equal, right? That's also entirely possible.
Okay.
Yeah.
I think we should probably stop now because there's lunch outside. So we'll see people are smiling at that. Yeah. So we'll stop there and thanks, Xuening, again.
Thank you.